That's exactly right.
Yeah, it's clearly right. It's like there's no possibility.
Okay, so these aren't molecules, so it's a little bit of a misnomer to say an intermolecular force. These are just noble gases, so they're individual atoms. That's okay though, because there's no other way that these can interact except through intermolecular forces like we've been talking about. So because they're not molecules, there is no potential for polarity, so it has to be dispersion forces. They are just atoms. They're nonpolar. Now, if they're all dispersion forces, let me finish my sentence, then I can't yet, or at least I don't know yet, how to predict strongest and weakest.
So I know hydrogen, like as itself, as a diatomic element, would have like a really weak connection.
Yes.
Is the hydrogen bond because it is such a like polar force?
Yes.
Is that why? So it's just like extra polar.
Yes.
So it's polar.
So like OH, you mean, not hydrogen with itself.
Right.
Yeah. So hydrogen with itself would be a dispersion force because it's nonpolar. The hydrogen bonding that we're talking about is nitrogen with hydrogen, oxygen with hydrogen, fluorine with hydrogen. And that's because it is the most polar bonds that we see that aren't ionic. And it also, I didn't say this before, or if I did, it's not required for you to know it. It's also because the atoms are really small. So because they're really small, they can also get really close to each other, which allows, when you have one molecule and another molecule that can get really close, then that force is going to be really strong too. Okay, the way that I can label these as weakest and strongest, even though we haven't talked yet about how to know within dispersion forces which ones are weakest and strongest, is because I have the boiling points. So if I have a low boiling point, that tells me that these are relatively weak compared to this higher boiling point. That's telling me that those are relatively not strong, but stronger than the ones above. Okay, so that's how I knew about the strength of the intermolecular force without even knowing what causes that yet. What does cause it is that those little temporary dipoles that come about in dispersion forces. So if you remember from these pictures above, right, these are not permanent partial positive, partial negative. They are just temporary. They come about because of the movement of electrons. Well, the bigger the atom is, or molecule, the more electrons it has. And by bigger, I mean more electrons. More nucleus means more electrons. More protons means more electrons. That also means a higher mass. So usually we talk about this as just being a higher mass, but that does translate into more electrons. So if you have more electrons, that movement can cause a larger temporary partial positive and partial negative. So maybe up with helium, it's like teeny tiny, right? And these ones are still small compared to something like water or even a polar molecule, but they're getting bigger because they have more electrons, more ability for them to shift around and move around and be manipulated by any neighboring charge. So that's the trend that you need to be familiar with, is as the mass increases, we're going to see an increase in the dispersion force. Okay, so another example of this, all of these compounds come out of the ground when you take fossil fuels out of the ground. So we talk about this as crude oil, but really it's a bunch of different compounds. So we can include like methane down here, CH4, and ethane, C2H6, okay? So CH4 is the primary component of natural gas, like your furnace, your stove, that's burning CH4. And those are gases. We just said that. It's natural gas, we observe it like that. Octane, this is the main component of gasoline, which is a liquid. It's kind of stupid that we call it gasoline, right? Because it's a liquid. My husband's a little neurotic about that. He'll be like, you have to either call it gasoline. You can't say I'm going to get gas because it's not a gas. You can say fuel or gasoline. He likes to say fuel, though. Big nerd. Okay, you also get really, really big carbon-hydrogen compounds. Oh, this is an important note. When the molecule only has carbons and hydrogens, you immediately know that it's nonpolar. You don't need to draw anything out. Carbon and hydrogen bond is so minimally polar, and the structure of it, the whole molecule is going to be nonpolar. So when I look at these, I know that these are dispersion forces. What I'm just looking at is what is the trend here in how their boiling points go. So I was saying C 30, 40, now we're talking about like asphalt and like nasty tar and stuff. So these are solids at room temperature. So all of that crud that we're getting out of the earth has a big variety of molar masses. The small ones have very low boiling points, and so at room temperature, they're gases. The bigger ones, like octane and all of that general area, have, excuse me, have slightly more mass, and so their boiling points are above room temperature, so they haven't yet boiled, right? They haven't turned into a gas yet. They're still a liquid. And then we get up to really, really big compounds, really big molar masses. They're already, in the solid phase. They haven't even had enough energy to melt at that point. Okay, so increasing mass, increasing boiling point, more of a tendency to be a solid at a given temperature. Okay with this? All right, let's do something similar for this one. Tell me what the intermolecular forces are, and tell me which one is strongest versus weakest. And then in this case, do try to explain these observed boiling points. Okay, so all of these are hydrogen bonding because they all have one of those OH groups. So this is what I mean by like, I'm not gonna make this too complicated on you as far as the structures and the molecules. Like if it's carbons and hydrogens, it's nonpolar. You don't even have to draw the Lewis structure, okay? If there is either an OH group written on the structure or even if it just writes it like this, that's telling you that that oxygen and hydrogen are bonded to each other. If they're bonded to each other, you know it's hydrogen bonding. If it's written like this, or probably would more likely be written like that, where all the hydrogens are paired up or grouped together and the oxygen's by itself, you can probably assume that that hydrogen is not bonded to the oxygen, that it's stuck to the carbon, not to the hydrogens. Okay, we are trying to indicate to you what the structure looks like by how we write the formula. Okay, so this one would be dipole-dipole, whereas this one would be hydrogen bonding. Okay, so they're all hydrogen bonding though. I can tell though that even though this one is a relatively strong force, it is the weakest of the three, because its boiling point is fairly low compared to the glycerin. So simply, the more of these hydrogen bonding sites that you have, this one you just have that one, here you have 2, here you have 3. The more of those you have, the more likely they are to create those strong forces and therefore be harder to break and therefore have higher boiling points. So ethanol, liquid at room temperature. Glycerin is a really thick liquid. So this is also called glycerol. This is what they generally put in like hand sanitizer to make it thicker. So you mix an alcohol with a bunch of glycerin. The alcohol is the thing killing the bacteria. The glycerin is making it like, you know, so you can rub it into your hands. Because if you just pour a liquid out, that's going to be a little messy and awkward. During COVID, when there was like a shortage of hand sanitizer, I actually like went on Amazon and like bought a few bottles of glycerin. And I was like, I'll just buy a bottle of vodka and I'll like mix it up with the glycerin or something. Because they actually were at that point where they were running out of isopropyl alcohol. So they started like distilleries started like selling hand sanitizer.
That's fantastic.
It was such a bizarre time.
It made the room smell so bad.
Yeah. You're like, who's been drinking?
High school had a bunch of it.
That's so
That's
bizarre.
so
The craziest thing was the wiping the groceries,
Oh yeah, I remember.
which was like, this is ridiculous. Like now we know like, it's probably not living on those groceries for very long. Anyway. All right. The last thing we need to talk about is how ionic compounds get involved in this. So the primary time we're going to see this is when they dissolve in water. So I can't remember if we talked about this when we first talked about solutions last semester, but we'll talk about it again in the next unit. But things that are polar dissolve with things that are polar. So you're not going to get octane mixing with water, gasoline and water. They're not going to mix because this one's polar, hydrogen bonding. This one's dispersion forces. Basically, the water would rather interact with itself because it's a stronger force than with the dispersion force thing. That's not going to be very strong. When we bring ions into it, they behave even more or even stronger than a hydrogen bond would. Now, this is a little bit different because we're used to talking about the same molecules, right? Like water and water. Now we're talking about a different species and water. So two different things. But we can still talk about their strength because remember, the only thing is how big are the positives and negatives. If they're teeny tiny, then the force is going to be very weak. If they start to get bigger, then the force is going to be stronger. And in this case, we've now gotten to the point where we have relatively big partial positives and partial negatives because it's a hydrogen bonding situation. We've got a very polar bond. And we're going to start having it interact with a full negative and a full positive. So that interaction between an ion and a polar molecule that's capable of hydrogen bonding is very strong. So this is why a lot of ionic compounds will dissolve in water, is because they're able to form this strong interaction with the water because they've got that full negative or full positive charge that then interacts with the partial charge of the water. And this is even stronger than a typical hydrogen bonding would be. I can't remember also if we talked about this in Chem 1, but good reminder. Water molecules will actually orient themselves so that they are pointing their positive side towards the negative chlorine, and then they're pointing their negative side towards the sodium. It's more complicated when we start talking about soaps, but it's actually a similar process. You'll get, no, I'm not going to go into it. If you're interested, I can explain it to you, or it is in the book, maybe at the end of this chapter, micelles. But that's where you get like a long chain that's nonpolar, dispersion forces, and then you have a group over here that's capable of hydrogen bonding. So one side will interact with the water and one side will interact with the oil that you're trying to clean off. And they do this orientation thing that's really similar to a salt as well. Which is why hard water makes your soap not work as good, because it takes up some of these water molecules and surrounds them around the ions. You were fascinated by that? My parents like over soften their water. So they have a water softener, and I swear it does too much. So like you feel like there's still soap on your body when you're in the shower, and you're like, I can't get it off. I feel slimy. All right. Okay, these next few sections talk about a bunch of different properties that are related to intermolecular forces. And I'm going to give it away right here, is that all but one of them increase this property that we're going to talk about, each of these properties, when they will increase with increasing intermolecular force strength. So there is only one of them. We call it a few different things: vapor pressure or rate of vaporization. That one is going to be opposite. So it's going to decrease with increasing intermolecular force strength. But all of the others, the stronger the intermolecular force is, the stronger this property is going to be. So surface tension, viscosity, heats of vaporization. We're going to do those today. Okay, so first one, surface tension. So this is not the same thing as floating in the sense of like, why does a boat float? That has to do with buoyancy and how much water you're displacing versus the weight of the vessel. So that's not the same thing as this. We're not talking about actually penetrating the surface of the liquid. We're talking about allowing something to sit on the surface of a liquid. So this results from the forces that exist between the molecules on the surface of a liquid. And those interactions, those are still the intermolecular forces. In the case of water, it's hydrogen bonding. Those surface forces, though, are much stronger than the forces that are in the interior of the liquid. So if you have one molecule in the middle and you have a bunch of molecules surrounding it, it's basically like the forces that it can exert are spread over a ton of different molecules. Whereas if you have one on the surface, it's connected to a lot fewer. And so its force is spread over fewer areas. And so these forces end up being stronger than the ones that are on the inside. So that's why this property results just on the surface of the liquid. If you're comparing it between two different chemicals, so we used the example of nail polish remover the other day, acetone. Okay, so this one is dipole-dipole forces, polar molecule, but not hydrogen bonding, versus water. Okay, you're gonna have a pretty hard time floating a paperclip on acetone versus on water. Insects can like land on water for this reason as well. I think there's like some kind of I don't know what it is, some kind of a insect. Okay, it's not gonna work. I'm gonna have to Google it. It's got like a Jesus something because it walks on the water.
Is that the lizard?
Is it a lizard?
The one that like
There's a basilisk
Okay.
lizard that runs in water. And that does it with little slits in its feet that trap air bubbles. So it's not
Oh.
exactly surface pressure, surface tension. I mean. And then there's water striders. There are a couple other species of beetles
Apparently
that
there are
do
a
it,
lot
and
of
fishing
them.
spiders.
Oh, well, there you go. Okay, then. Now we know. I bet a lot of it, even if you're talking about air bubbles that it has, I bet a lot of it's still due to the fact that it's, like if you had a liquid that had lower surface tension, it probably wouldn't work. Yeah. Okay, so the ones on the surface are stronger, but they have to be relatively strong. So if you have a liquid that has weaker intermolecular forces, this isn't going to work. Okay, so stronger intermolecular forces, higher surface tension. We're going to keep seeing that. Stronger intermolecular forces is going to increase all of these properties, except for that one. Okay, next one, viscosity. You can basically think of this as thickness of a liquid. I feel like somebody asked about this a couple days ago. So let's go back to the glycerin example. So think about pouring water versus pouring hand sanitizer, right? The reason why the hand sanitizer is thicker or pours more slowly, so resistance to flow is the technical definition of viscosity. So the reason why that doesn't flow as easily is because most of it is glycerin. Well, not most, but a good fraction of it is glycerin. And so those intermolecular forces, because of those additional hydrogen bonding sites, allow it to be thicker and hold together more. If you think of like, a container of it where it's got all these forces holding it together, and then you try to pour it into this thin stream, you're having to actually break some of those intermolecular forces as you pour it. So the weaker they are, the easier it's gonna be to pour. I had a professor that I did research for, and he said that the mark of a good chemist is the ability to pour without spilling. Because you can judge the viscosity well enough to know how, and that's dumb. Kind of true though. You never want to touch the two containers to each other. That's a recipe for spilling. Because then you start to get the forces interacting with the container themselves. So you want to separate them and get a thin line. Okay, so same thing as we talked about before with carbon-hydrogen compounds. The bigger they get, the higher viscosity we see. But this is still significantly less than water. So octane, viscosity of about 0.5. Water's viscosity is set at 1. We kind of mark everything off of water. So you see it increasing as the as the dispersion force is increasing, but you also see that the hydrogen bonding one is significantly greater.
I found the Jesus critter you were talking about.
Yeah? Is it a lizard?
It is the lizard.
Oh, okay. Good job. Olivia.
I
Oh, okay. Well, good job to give credit where it's deserved.
Yeah, she typed in uncommon basilisk. Yeah, I had basilisk lizard.
Basilisk?
Yeah, it's a basilisk.
Oh, like in Harry Potter.
Like in Harry Potter, but it's a lizard.
Sorry, Laws of Harry Potter.
So yeah, it doesn't kill you.
Okay.
They're cute little guys. They got cool crests though.
All right. I'll have to Google it. Okay, so the next one that increases with increasing intermolecular forces is the energy required for a phase change to occur. Now, we've kind of implied this already by saying that boiling points and melting points have to be higher. It's basically the same thing, but slightly different. On Monday, we'll get into what process actually is involved in taking like an ice cube that's at, let's say, negative 10 degrees and warming it up, melting it, and then turning it into a liquid that's at 25 degrees. There's kind of multiple processes there. There's like heating it up, there's the melting part, and then there's the heating it up again. So we're specifically talking about the melting part or the boiling part, not the heating up part that would have to happen first. Okay, so now that I just said that, let's go ahead and label these. So this is melting. I think I missed an L there. Melting. And then this going from the liquid to the gas would be boiling or evaporation. And then the reverse sides of those would be freezing, going from the solid to the liquid, and condensation, going from, or condensing, I guess, going from the gas to the liquid. We'll talk about the other one too at some point here, going from a gas to a solid and then going from a solid to a gas. This one's called sublimation. So it'd be like what CO2 does at room temperature. And deposition is the gas turning back into a solid.
Would I be annoying if I asked you to explain that again? Can you explain that's like just the red arrows and the blue arrows?
Yeah, so the red ones are going from the solid or liquid form up the scale of solid to liquid to gas. And then the blue ones are going back down the scale. Let's talk about the energy component. I think it'll make more sense too. For some reason, that should not be there. That should say released. The other blue one says released. Okay, so the red ones, we're breaking intermolecular forces there. And so that's going to require energy. So another way we can say that now that we've talked about energy changes is that it's endothermic, right? It requires energy, or energy has to go into it. And we will even talk about it as an enthalpy value being positive. Yeah.
So is this why when you sweat you cool off?
So yes, that's the opposite. So let's use that. That's a great example. We'll use that for this one. So when you're sweating, no, you're right. It is the same example. It's from liquid to gas. So you've got a liquid on you, your sweat or water or whatever, and it requires energy for it to evaporate, and it takes the energy from your skin. The other direction is why steam will burn you worse than water. So when you go from a gas to a liquid, energy is released. So if you stick your arm over a pot of boiling water and the steam hits you, the energy is released onto your skin. So 100-degree water versus 100-degree steam, the steam is actually going to burn you worse. So that one is exothermic, because energy is being released, or would have a delta H that's negative. And that's because those intermolecular forces are forming. So as they form, you're bringing those interactions together, you're lowering the potential energy, and that energy goes off. We could even draw like energy diagrams. I didn't do this in my other class. But you've got like a gas to a liquid to a solid. This would be the potential energy changes. Whereas up here, you would have the solid to liquid to gas. There was something else I was thinking about. I'm trying to remember what it was. Oh, we're going to talk about this well, I'll just bring it up in a second. Lily, did you have another question?
Yes. So I know large bodies of water contain a lot of energy, right?
Yes.
Which means that would that mean that the air temperature is more stable closer to a large body of water than?
Well, I mean, observationally, we see that's true, right? Like, even though, England is really far north latitude, they have relatively mild temperature swings. I want to say they just barely get below freezing, and then it's also not particularly hot there. And I think that's because it's an island, and so it's around the water. Is that due to the fact that the air temperature is like, what's the right word? Not modified, but like,
Impacted?
no, like so that it stays in a particular range. Stabilized. Yeah. Probably. So the reason why the water holds on to the heat well is because of specific heat capacity. So it has a high heat capacity, and so it's going to take a lot of a removal of heat in order to get the water to change temperature at all. I'm thinking about how that was. So air itself has a very low specific heat capacity. It cannot hold on to energy very well. But if you were to get cold air next to water that has some heat in it, then the water could definitely moderate. It's the same reason why in a desert temperatures drop really rapidly. Yes. Because it's the same reason why in a desert temperatures drop really rapidly at night, because most of that energy is being provided by the sun. Whereas we were talking about this the other day, in a humid place, your temperature only drops very low at night because the water is holding on to that energy that came in during the day. Yeah.
So for this, would the gas be colder than the liquid since it's giving up energy? Like if we could touch the gas, it would feel colder than the liquid?
Well, so once you touch it, no, it would be the same temperature. So my daughter actually asked about this morning, and I have no idea where. Oh, she said it was like from Family and Consumer Science. They were talking about like cooking things. So I said, no, you can't get water above 100 degrees Celsius. Like, there is no boiling water at that point. It's going to turn into a gas. So the more energy you put into it will never increase the temperature. So as long as the gas is just barely out of the liquid phase, they will be the same temperature, but it holds more heat because of the intermolecular forces. More though, not less. So
Gas holds more heat?
yes. So the temperature will be the same, molecule for molecule or mole for mole or whatever. So the temperature would be the same, but there would be heat energy contained in the gas that then would get released when this process happened here. So like if this is 100 degrees and this is at 100 degrees, when that transition happens, heat will come off and burn you. So we will actually do charts like this where we'll say, how much energy does it take to warm the thing up? How much energy does it take to convert it to a different phase? How much energy does it then take to warm it up even more?
On the pre-chapter assignment, we saw like a really interesting graph with like fields for gas, liquid, and solid.
Did it look just like this?
No, it was kind of like
Oh.
a curved line, and they were like shaded.
Oh, phase diagrams. Like this.
Yeah, like that.
Yeah.
Exactly.
Yeah.
So I had a question on one of those, and I think it's kind of related to what we're talking about right now, where it went through all three, but like ended up in like the gas phase.
Mm-hmm.
And the question was like something silly like, which one does it, go through? And so, you answer all three, and it's like, no, it's wrong. And I want to know why.
Well, now I'm going to have to go look at the question. So let me make you do a calculation, and I'll go look at the question while you're doing the calculation. Okay, so there is an actual quantity related to these phase changes. So on this next slide, it gives you the example of xenon, and it gives you the delta H, the enthalpy of fusion. So fusion is going, this specifically because it's positive, is going to be going from a solid to a liquid. And then vaporization, this is going to be going from a liquid to a gas. Don't ask me why we call it fusion. If you're melting it, to me, that's the opposite, but whatever. If you wanted to do the reverse reaction, what happens to an enthalpy value if we flip the equation around? It gets negative. It changes sign. So if you wanted to do the reverse reaction, liquid to solid, it's going to be the same number. It's just going to be negative. So gas to liquid, same thing. It's going to be negative 12.64. So we could actually put these on the thing. We could say this one is the delta H of vaporization. We still call it vaporization, even if it's the reverse direction. We don't call the process vaporization, but we call the value vaporization. We just change the sign. And then delta H of fusion, negative 2.294. So I'm just putting these in specifically to show you this one. These numbers are for xenon, but this is specifically to show you where those quantities correspond to. So melting is the delta H of fusion. It's going to require, so positive, 2.294 kilojoules to convert 1 mole from the solid to the liquid. So same numbers, just different signs for those phase changes depending on which direction you're going. And these will increase with increasing intermolecular force strength. So the energy that is required to go from a solid to a liquid to a gas, or the delta H of fusion, the delta H of vaporization, those quantities will increase the stronger the intermolecular forces are. I want to say that the delta H of vaporization of water is like in the thousands of kilojoules. Maybe it's hundreds, but it's certainly significantly more than 12 for xenon, which is dispersion forces. Okay, so you're going to take these values, and I want you to tell me if I have 2.3 moles of xenon, how much energy, kilojoules, is going to be required to take that amount of moles from a liquid to a gas. And I'm going to go look at that question now. Taking a ridiculous amount of effort on my phone, but I'm almost there. Because it says which statement is not true. Is that possible, Lily?
That could be entirely I just had a hard time reading instructions.
That's okay. All right, so liquid to gas is going to be the vaporization one, so 12.64. And it should be positive because we're going up in the phases, right? We're requiring energy. And then you do it just like a normal dimensional analysis conversion factor type of thing. The moles goes on bottom. That's how you know you're going to multiply it. So 12.64 times 2.3 or 29 kilojoules. And then I'm not going to do the next one because we're a little low on time. Or maybe I'll do it for you guys to check your work when you're doing the next problem. Okay, so you need to first do a mole conversion. No, I am doing it apparently. And then this one is going from a liquid to a solid. So this should be negative. It should be releasing energy. So negative 2.297 per mole. So gram to mole first. If you are shaky on that, you got to go review it. That is non-negotiable. So negative 1.85 kilojoules here. How did I know it was negative? Because I know that a liquid to a solid is releasing energy. So I have to choose to make that negative. It's because I flipped the reaction around. It's the other way to think about it. Okay, the last thing we want to do, booger. Yeah, we can do this as a warm-up on Monday if we need to. Okay, so the last thing we need to talk about is vaporization, which is the one thing that is opposite the strength of the intermolecular forces. So the stronger the intermolecular forces are, the less vaporization you're going to see happening. So vaporization is just like a formal term for evaporation. So it is going from the liquid to the gas phase, not at the boiling point. So before you get to the boiling point. So there's basically a distribution of energies of all the particles. And so in any given temperature, there is a small fraction of the particles that have adequate energy to break the intermolecular forces and turn into a gas. Once you get to the boiling point, you're basically saying now that all of them have adequate energy to do that. Prior to that, you have some, though, that have enough energy, and typically they're at the surface. Okay? So the stronger those intermolecular forces are, though, the harder it's going to be for there to be some that have adequate energy. So you've got nail polish remover and water. Nail polish remover is going to evaporate much more readily because it has weaker intermolecular forces. There's enough energy in the room to make those molecules have be able to break those forces. Okay? Yeah.
And when we're discussing like energy in an area, are we discussing like loose electrons? Like what is energy in this context?
Heat.
Okay.
Yeah. Kinetic energy. Energy of motion. So we're talking about literally motion in the air molecules surrounding it or in the water molecules. Good clarification. Okay, we have 2 or 3 minutes, so we're going to do this. All right. All of these properties, I'm going to tell you already, every single one of these, because we just talked about them, the lowest should be the ones with the lowest of these properties, lowest surface tension, lowest viscosity, should be the weakest intermolecular forces. And the highest should be the strongest intermolecular forces, simply because we don't have vaporization on there. So all of these other ones should increase with increasing strength of intermolecular forces. The strongest one on that list, this guy. This is hydrogen bonding because I got that OH group on there. This one is dipole-dipole. I know that because that oxygen immediately I know is going to make it polar, but it's not connected to a hydrogen. CO2 I know is dispersion forces because I've looked at it a million times. And a CH compound is always dispersion forces. So I know that the C2H5OH should be on the high end, high viscosity, high surface tension, high melting point, lots of energy to make the phase changes happen. And I know that the C3H8 and the CO2 should be on the weak end. And the C2H4O should be in the middle. Now, I should have given us an example where we could have differentiated those two. I added them up and they literally have the exact same molar mass. They're both 44. So, oops. Next time we'll pick a different one, CH4 or something. Okay? All right. That's it. I'll see you guys on Monday.
Tylenol.
Yeah.
I have some.
Yeah.
I appreciate you. I have to get a root canal.
Do you really want Tylenol though?
I can't take anything else. I have ulcerative colitis. and
Oh,
that
gosh.
Makes me like blood thinners. Yeah.
I have one.
That's fine.
Okay.
That's completely so fine. Thank you so much.
Yeah. I have a caffeine pill, but it looks like you got that covered there.
Yes, always.
I also have a lorazepam, but I'm not going to give you
Is that for
that.
anxiety?
Yeah.
I got that covered too. Thank you.
I have a quick question.
Yeah.
So I noticed in Blackboard that like
Don't look at your Blackboard grades.
Don't look at, okay.
Yeah.
Okay.
Only look at Pearson grades. I'm never going to try to sync the grades now because it never comes across.
Okay.
So if you go into Pearson, you should be able to just see your total grade there.
Okay. I was worried, but I'm
I
no
know.
longer worried. Okay.
I know.
Thank you.
Yep.
Have a good weekend.
You too.
Thank you again.
When are you having your root canal?
Right now. I don't even know. Like, it's always something, I swear.
That's like, and it just gets worse.
Yeah. Like, I have to go to Children's every 8 weeks for my infusions for my colitis. So, like,
Aren't you a little old for that? For children still?
they kicked me out when I'm 20.
Oh.
22.
Oh.